Thanks, Madam President and members of the Board of Examiners. And I'm Ophélie Renaud, a PhD student at INSAREN, supervised by Jean-François Nezan and Carole Desnos. And today, I'm going to present my last 3 years of research, entitled Model-Based Granularity Optimization for High-Performance Computing System in Astronomy. And this work was supported by Einer Darker. So the context of this thesis is the radio telescope under development SCA. SCA consists of antennas in South Africa and in Australia that capture sky signal and process them through a processing pipeline in order to generate output image. The SCA is composed of two main parts. The CSP, which stands for a Central Signal Processor, converts antenna voltages into visibilities. And the second part, the STP, which stands for Science Data Processor, converts the visibility into output image. And the SCA, because of its huge collecting surface, generates a huge quantity of data. And because of storage constraints, this data has to be processed as fast as possible. So this raises huge problem in a huge challenge in parallel programming. So astronomers are experts in their field, but less so in parallel programming. They are actively developing their increasingly complex algorithm in order to convert the antenna voltages into image of the sky. And this algorithm has to be deployed or not yet built HPC system. And the system has to meet the real-time constraints imposed by the radio telescope SCA. And this challenge will lead to the question that will unfold this presentation, which is how to optimize the execution of a program as complex as astronomical on a system as complex as HPC. So this is where rapid prototyping comes in. So rapid prototyping consists in creating a functional version of a program as fast as possible to facilitate the development of an application further later. And Prism, developed at IETR since 2008, is one of such tools. And initially, Prism was created to support embedded systems. And during my thesis, I extended it to support HPC systems to better serve the need of astronomers, among others. And so to understand how, I start to introduce the resource allocation challenges at any scale. So, as you may know, modern architecture are becoming more and more complex, which on the paper improve the application performance, but are hard to follow for developers. This introduces a software productivity gap. And to address this gap, we employ a graph-based algorithm architecture adequation method. And this approach consists in modeling both the architecture and the application as two graphs, then apply some graph transformation in order to align this graph. This is called adéquation in French, which means matching in English. And the result is an optimized parallel code. So in the application side, an effective model is a data flow model. The data flow consists in a graph where node, also called actor, represent computation, and edge represents the FIFO buffer. And an extension of the data flow is the synchronous data flow, where there is integer on the port factor that represents the rate of token produced and consumed by an actor. And an extension of this extension is the PSDF, which integrates the hierarchy So an actor, instead of being specified by a C code, is specified by a subgraph. And this model also describes the rate with parameter to describe rate with an expression. So this model admits several advantages, like expressing several types of parallelism. For example, task parallelism consists in executing simultaneously several actors at the same time. For example, here, actor A and actor B can be executed simultaneously on two processing elements. The data parallelism consists in executing simultaneously several instances of the same actor if there is enough data token at the input of an actor. For example, here, two instances of actor C can be executed simultaneously. And finally, pipeline parallelism consists in breaking graph dependency, dividing a graph into several executable stages. For example, here the first stage is composed of vector A, B, and C, and a second stage is composed of vector D and E. So this is done thanks to a delay, which is a node that will contain initial data token at the first graph iteration, and then save the token from the previous graph iteration. And another advantage of the model is that it is architecture independent, which means that the developer has to specify an algorithm only once to be portable on any target architecture. And in the architecture side, we employed the SLAM model, which consists in representing architecture with a very simplified model at system level. And here, a graph is composed of processing element, communication node, connection types, and properties. And the SLAM allows to represent at least two memory architecture. So, for example, shared memory consists in all processing elements communicate through a common memory. And in opposite, distributed memory, all processing element has its own local memory and communicate through a network. So, well, now that we have both the application and the architecture as two graph, let's talk about matching. And matching consists in allocating resources. And the standard data flow resource allocation only focus on CPU target architecture and involved in this step. First, flattening consists in putting all the all actors at the same level, replacing all hierarchical actors by their contents. Then the DAG will reveal parallelism and communication by duplicating all the actors by the number of times they are repeated at each graph iteration, and adding special actors that will gather or distribute token on a regular actor. Then the process proceeds by mapping, which consists in placing all elements of the DAG on processing element. Scheduling consists on ordering this element of the DAG on the processing element, and timing consists in associating a start time and an end time to each element on the processing element. Then the process will translate the element on a parallel code. But there is a major issue with the standard data flow resource allocation is that the time to allocate resource increase exponentially with both the architecture and the application graph. As illustrated here. Here, the axis represents the resource allocation time according to the number of actors of the application in red, and the resource allocation time according to the number of processing elements of the architecture in blue. And for both, the exponential trend is clearly visible. And so this problem is obviously not compatible with the SCA objective. And so in order to answer to the leading question, I will provide a solution to improve the compilation of the program vertically, to improve the execution of a program on parallel target architecture, to provide reliable simulation, and to provide simulation on large-scale architecture. And now let's talk about contributions. So we aim to propose astronomers a tool that allocates resources and design the HPC system that work all by itself. So to do so, we need to optimize the resource allocation within a single node first before scaling things up. So this is our first contribution. So the aim of our first contribution is to reduce the resource allocation time within a single node without compromising the execution of an application on the parallel target and even reducing its execution time. So back to the standard resource allocation. So sometimes the parallelism of an application doesn't match the parallelism of target architecture. For example, here the actor B can be parallelized on 4 processing elements, but we only have 2 processing elements. So the standard resource allocation will overexpose parallelism, which is not necessary in this case. And an effective way to simplify a graph is clustering. And clustering consists in grouping actors together following clustering rule in order to avoid deadlock. And for example, here we cluster 2 actor B and 1 actor C into a single actor omega, which will repeat twice in order to preserve the graph consistency, reducing the size of the SDF graph from 7 to 3 actors, and reducing the complexity of the DAG from 10 to 4 actors. And this will significantly accelerate the mapping scheduling process time. But uncontrolled clustering leads to sequential application. So this is where our contribution happened. So our contribution was the purpose of 3 contributions, but I will just explain the first contribution, which is called scale, for scaling up of cluster on of factor on processing elements. And the method happens upstream of the standard resource allocation process and aims to simplify the graph while preserving and or improving the necessary parallelism. And consists in identifying particular pattern of actor, isolate them in a subgraph, and playing with the token in order to match the repetition of the hierarchical actor to the number of processing elements. Then, given that the graph will be mapped to a single processing element, it's easy to compute its schedule. And then we translate this element into code where for loop correspond to the repetition of the actor subgraph, and the actor are translated into function calls. Then this newly generated code will replace the subgraph, and then the standard resource allocation proceed with this simplified and optimized graph. So, and what differentiates the two first versions of our method scape is the identification of particular pattern of actor. And the first version focus on reducing the excessive data parallelism to match the target. And the first pattern is URC, which stands for unique repetition count. So this corresponds to a same sequential actor with that share the same repetition vector. For example, the method will group actor B and C together and then match the repetition to the target. Here, reducing the size of the SDF graph from 17 actors to 5, and while preserving the parallelism of the target picture. The second pattern focusing on data parallelism is SRV, which stands for single repetition vector and consists in an isolated actor with a repetition greater than the target. And the process is the same as the previous one. We group this actor and match its repetition to the target. Here, reducing the size of the SDF from 10 actors to 6 actors while preserving the parallelism. So the first version of Scape take as input the data flow graph and one parameter, one integer that corresponds to the level of clustering, and provide in output a set of clustering configuration to allow the user to choose the wanted granularity. And the number of clustering configuration equals the number of hierarchical level plus 2. As an example, here, the graph, there is 2 levels. So the number of clustering configuration equals 4. The level 0 of clustering corresponds to the input graph without any clustering optimization. The level 1 consists in identifying particular pattern on the subgraph only. And the level 2 of clustering corresponds in grouping the subgraph coarsely, and then identifying a particular pattern on the top graph. That's it. And the last one consists in grouping the entire graph into a single actor omega, which sensibly facilitates the mapping but makes the application fully sequential. So to clarify, there is a 3-scape method, each extension of the previous one. The first version of Scape focus on reducing data parallelism on the target architecture. The second one extend the first one by increasing pipeline parallelism, identifying a sequential part of the graph thanks to clustering. And the final one allow pattern matching on all admissible hierarchical level, leading to only one clustering configuration fine-tuned to the target architecture. So I'm going to compare the 3 versions of Scape with the method without any clustering optimization. Here, the axis represents the resource allocation time according to the number of processing elements. The lower, the better, and all Scape accelerates the process of allocating resources. And here for the performance, so here the axis represents the throughput speedup according to the number of processing elements, and the higher the better. And we can see that the without and Scape 1, the both curves overlap because we preserve parallelism. And Scape 2 and 3 improve performance since we add pipeline on sequential path. And here, the axis represents the average data transfer time according to the number of processing elements. And we can, the lower the better. And we can see that all Scape method reduces communication overheads. And average, here the axis represents the average synchronization time according to the number of processing elements. The lower, the better, and the same all-skip method reduce the synchronization overhead. So to summarize this first contribution, I introduce a clustering method to optimize resource allocation within a single node, so that improve mapping choice, reduce resource allocation time, reduce communication and synchronization overhead, but is limited to a single node target architecture. And the method was the purpose of 3 international papers. So, well, now that we have optimized resource allocation within a single node, let's move on to the next step, which is allocating resources on multi-node architecture, which leads to HPC system. This contribution was initially motivated by collaboration with 2 partners. So the astronomer at CSIRO at Inday and the IRISA laboratory. And our aim is to provide a HPC multi-node resource allocation method. So to do so, we take advantage of the SLAM model to represent homogeneity. So a node is homogeneous if all processing elements share the same characteristic. In opposite, heterogeneity, a node is heterogeneous if the processing element doesn't share the same characteristic. For example, if 2 CPU cores operate at different frequencies, this makes the node heterogeneous. And I implemented into Prism a way to model a multi-node architecture. So a multi-node is an architecture composed of several interconnected nodes, which lead to the structure of HPC system. So the proposed method takes as input the data flow model and the multi-node SLAM model. Targets balanced workload partitioning between nodes and provide a HPC code. So the method is iterative since we have 2 levels of resource allocation within a single node and on the overall system. So the method is composed of 3 main steps. So the node partitioning consists in dividing a graph into subgraphs. Each subgraph is associated to a node. Then we employ scape on each node and each subgraph to optimize the resource allocation within a node, adjusting the granularity. And then we simulate the intranode and the internode behavior with a combination of 2 tools, Prism from IETR and simulate from IRISA. And then we, with the single feedback of workload partitioning, we readjust the construction of subgraph in order to reach balanced workload between nodes. So the method deals with standard heterogeneity. So standard because we only with CPU target architecture. And here we consider the different frequency operating frequencies and the number of core per node that will vary between nodes. So in order to achieve a balanced workload, we estimate the workload. And to group, in order to manage heterogeneity, we group the 2 parameters into one single, which is a number of equivalent core, which correspond to summing the frequency ratio between cores. And then to estimate the workload. So the estimated workload, we play with the proportion between the sequential execution time of the application and the number of equivalent core per subgraph. And then we construct the subgraph, adding the actor following the special order to reach this estimated workload. As a use case, I model RFI filter, an astronomical application. So the application take as input a noisy signal, compute some threshold, and remove the noisy signals. So the data flow model is massively parallel, and I can easily play with the complexity of the graph with the size of the input file. So I'm going to deploy the RFI filter on 3 multi-node architecture. The first one is homogeneous. The second one, only the frequency varies. And the third one, only the number of cores per node varies. And here, the axis represents the resource allocation time according to the architecture deploying the RFI filter. And for all the case, for one iteration of the method, take just a few minutes. And now the resource allocation time only depends on the complexity of a target architecture within nodes. And here to analyze the iterative impact of the method on various granularity, here the axis represents the latency according to the iteration of the method, comparing an application with a coarse granularity and a fine granularity. The lower the better. And we define coarse granularity with it's an application where communication, the time of communication is lower than the time of computation. And on a coarse granularity application, the method directly reaches the optimal and then oscillate around this minima. And in opposite, on fine granularity, the method take benefit of the iteration to find the a better latency. So to summarize, I introduce a clustering method to optimize resource allocation on multi-node target architecture. And we deployed and validated our method on the cluster grid 5000. But this method requires architecture specification that may not be cited for the application. And this method was the purpose of a scientific paper. So now that we've optimized resource allocation on multi-node target architecture, let's move on to the next step, which is designing the HPC system. So the method was motivated by collaboration with one partner, which is Eviden, for their expertise on HPC systems. And we aim to find the ideal architecture for a given application. And we define a HPC architecture by the number of nodes, the number of core per node, and the networks that connect nodes. And we want to find the one that gives the best latency, and we simulate the memory, the energy, and the cost. So to do so, we model the 5 main network topology employed with graph. So the first network is a cluster with crossbar. So that corresponds to a cluster where all nodes are connected to same switch. Cluster with a shared backbone, all nodes are connected to a central bar and share the same communication path. The torus cluster consists in a cluster where all nodes are connected to its neighbor. So it's an effective cluster for application with a regular pattern of communication. Factory cluster corresponds to a cluster where switches are organized on a row that allow redundant data paths and allow to achieve high bandwidth. And an alternative to factory is the Dragonfly cluster that reduce the surface area and the machine cost, and is characterized by a group of nodes. And to find the optimal parallelism is not so trivial. For example, here the axis represents the latency according to the number of processing elements. The lower, the better, deploying a DSP application. And the trend is asymptotic, but admit several local minima. And we want to find the global one without simulating all possible cases. So to do so, the method initiates with three initial simulation to estimate the need of an application and to set the boundary for the later for loop of simulation. The first one consists in simulating the application on a single core architecture to estimate the minimum memory required and estimate the minimal number of nodes to support the application. The second one consists in simulating the application with the maximal number of pipeline on it, on a single core architecture, which give theoretical maximal speedup. And finally, we simulate the maximal parallelism given by the speedup, theoretical maximal speedup that give a target latency. And then we enter in a for loop of simulation. And for each simulation, we recompute the parallelism boundaries, and we simulate the latency, memory, energy, and cost. And so the parallelism boundaries is defined such as the latency is no more decreasing for delta iteration to avoid local minima and to find the global one. So here the axis represent the memory versus the final latency versus the energy versus the cost with a pseudo exhaustive method for co-designing a DSP application. And here with our method. So we reduce the number of simulation from 72 to 22. Which reduce the co-design process time, and also we preserve more than half of the Pareto optimal architecture. And here to analyze the impact of the network, we compare the radar chart represents the cost, energy, final latency, and memory. Deploying DSP application on crossbar, backbone, Taurus, factory, and Dragonfly. And the largest coverage, the better. And here, for designing a small application, the best latency is obtained with a Taurus cluster, given that the small application has a regular pattern of communication, but a best compromise is obtained with a factory cluster. And here, with a bigger application, both the best latency and the best compromise is obtained with a Taurus cluster. This is because this application has a highly regular pattern of communication. But this result has to be taken with caution, since we generate a default routing. And this routing could be, as a future rock, integrating as a parameter to reach a better accurate, a better architecture. So to summarize this third method, I provide a method to co-design an HPC system that retrieves the best architecture, HPC architecture for a given application. And this work was the purpose of an international scientific paper. Until now, we only focus on a standard HPC system, which are system composed only of CPU target architecture. And now we extend our work on modern architecture, and for our case, that are composed of GPU. So this is our ongoing work, and it was motivated by collaboration with two partners, the Australian astronomer at Swinburne University and the CSIRO astronomers. And we want to allocate resources on modern heterogeneous architecture that are composed of CPU and GPU. I will not detail this method, just give an overview. So the method takes as input a special system level of architecture, which is a GSLA, and allow to represent internal algorithm that is better suited to represent GPU. And we extend our escape method to deal with GPU by identifying GPU-friendly pattern of factor, provide an analysis, and generate a curve for NVIDIA GPU accelerated architecture. And this work was carried out by the intern I supervise, so Ewan Michel, at Swinburne University and IETR as part of the Rising Star project. And now let's conclude. So I introduce several methods to provide for astronomers a method that optimize resource allocation and design the HPC system that works all by itself. So the three first methods are grouped on a single contribution and focus on optimizing resource allocation within a single node target architecture. The second contribution is a clustering method that optimizes resource allocation on multi-node target architecture. And the third contribution is a clustering method that finds the best HPC architecture for a given application. And our ongoing work optimizes resource allocation on GPU and CPU target architecture. And all these methods are implemented into our Prism tool and are available on GitHub. And all the methods are the purpose of international paper. And as a future work, we could improve resource allocation method for GPU accelerated architecture by adding a feature on the GSLA model. For example, we could integrate the cache size to improve the mapping choice. Another perspective is to improve data locality and cache utilization by automating the process of for loop reorganization, taking advantage of existing tools. For example, Scape could create or isolate a for loop. Then IESL or Pluto can reorganize the loop iteration, and then Apollo, that is already integrated in a Prism, can select the best for loop at runtime. And finally, as a future work, we could extend the resource allocation and co-design process on modern HPC system composed of GPU and FPGA. To do so, we could compute the number of equivalent core of GPU and FPGA, and then consider mapping restriction to map and partitioning the application on GPU or FPGA and other. So that's all for this presentation. Thank you for your attention.